imagine I take a sequence of numbers. Let's say A0. So I'm gonna always start my sequences from 0 because for some reasons that will kind of be hopefully natural. So I've got a sequence of infinite sequence of numbers, A0, A1, A2, etc. And then I can define the generating function of this sequence. So the sequence is called sigma for some reason. So I can define the generating function of sigma to be the sum from n equals 0 to infinity of an x to the power of n. So it's not supposed to be clear why we're interested in these generating functions yet, but this is just a definition, and then we'll see why these things are interesting and kind of useful as we go along. So in other words, so if I want to write this sum out kind of more explicitly, right? So in other words, it's a0 times 1 because it's, a0 times x to the 0. X to the 0 is 1 unless x equals 0, but let's not worry about that. A1 times x, a2 times x squared, a3 times x cubed, and so on. Okay, so it's just like if you're familiar with things like Taylor expansion, it's kind of like a Taylor expansion, but except instead of taking a function and saying what is the Taylor expansion, what we're going to do is take a sequence of numbers and just write out the expansion, and we call that a generating function. Is it clear what I'm talking about here? And so we're going to try to understand these generating functions and what they can say about sequences of numbers, what we can use them for, basically. Now, I want to be a little bit careful. So the word generating function is kind of unfortunate in the sense that a generating function, you can't always think of it as a function. So, in some sense, you can sort of think of a generating function as being a function where, f of x, you can just plug in for x, but that doesn't always really work because this infinite series where I add up a0 plus a1x, etc., it might not always converge. So that's one annoying thing about generating functions, is that it's not really a function because you can't always plug in values for x. So it's sort of more of a formal kind of object, which, let's not dwell on that too much, but sort of think of f of x as being a function, but be careful when you plug values in. That's, I guess, what I should say, because it doesn't always converge. The only time it does definitely converge is if I plug in 0, right? So if I can evaluate, so I can always plug in 0 because that just makes every term 0 except for the first one. So f of 0, we can always say is equal to a0. But if you plug in a different value for x, you have to be a bit careful, unfortunately. Okay, a question for the audience. This is actually related to the poll. So what is the generating function for this sequence? Okay, and of course, technically the generating function is, I'm not going to use the letter n because the letter n is already here. But technically, the generating function is going to be, n choose 0 times x to the 0 plus n choose 1 x to the 1 plus ... up to n choose n x to the n plus 0 times x to the n plus 1 plus 0 all the way after that. But can anyone give me a closed form expression for this function? So here I've written it as a sum, but it's also useful to think of it to say what is this function if I represent it as a closed form without a sum. Yeah, good. So someone notices this is the same thing we were dealing with in the poll, right? So this is 1 plus x to the n. Okay. So this is just an example. So this is an example we've seen before. This is the example that comes from the binomial theorem. So if I have a finite sequence, which is just the binomial coefficients of n, then the generating function is 1 plus x to the n. Okay, now here's a nice question. I'm not sure, maybe some of you have seen this before, maybe some of you haven't. What's the generating function of the infinite sequence 1, 1, 1, 1, 1, 1, 1 forever? So just the sequence which is all equal to 1. And of course, like the easy answer always is to just write the sum because, that's always correct. So, I mean, so I can just write the sum so all of the ANs are equal to 1. So it's just the sum of x to the n. But what I'm kind of more interested in is not just like what is the generating function written as a sum, but, what is the closed form of this sum? So in other words, I want to write it in a way that doesn't involve an infinite sum. Does anyone already know the answer to this? If I take the sum of the nth power of x. And by the way, a little bit of terminology is that we call this infinite sum of the powers of x. So it has a special name. It's called the infinite geometric series. So if you take, yeah, that's right. So we're going to derive that. So there's a formula written in the chat, which we're going to derive in a moment. But yes, and also it's important that this formula is only valid when it converges. Okay, so when I say infinite, like whenever you hear the word geometric series, you should always think of this kind of a sum. So this is the infinite geometric series where the base of the whatever is x. Okay, so geometric series is just the powers of a number added up over all the different powers. Okay, so how can I derive that closed form that was written in the chat? And there's a really nice trick, which I think it's a really, really kind of cute trick, and you need to know how to do these kinds of manipulations. So this type of thing is something I would suggest you get familiar with. Okay, so f of x is just the infinite geometric series. So it's 1 plus x squared, etc., x cubed, and so on. What happens if I take x times f of x? Now here we're assuming this converges, sort of. Okay, so if I assume that this converges, what happens if I take x times f of x? Well, it's like x times this whole sum. And of course, we know how multiplication works. So this x can go inside and multiply to everything inside. So that's the same as x plus x squared plus x cubed, x to the 4, and so on. So what happens if I take f of x minus x times f of x? Any thoughts? So the point is there's a lot of cancellation. Yeah, exactly. You're just going to get 1 because if you think about it, you've got, 1 plus x squared plus x cubed, etc. ... And then I subtract x plus x squared plus x cubed plus ... And you can see that I'm subtracting like all of the, this x, for example, gets canceled by this negative x. And this x squared gets canceled by this negative x squared because there's a minus here, right? And everything cancels except for the first term, the 1. So it just equals 1. Again, this is all under the assumption that it converges, which, but formally, it's kind of okay. But anyway, so if I factor out the f of x here, I get f of x times 1 minus x is equal to 1. And so if I divide by 1 minus x, I get that f of x is equal to 1 over 1 minus x. So the fact that this geometric series is equal to 1 over 1 minus x, so these things are equal, I would really suggest to remember this, okay? It's also good if you know how to derive it the way we've done here. So deriving it is also it's a very valuable exercise, but I really suggest remembering that formula. It's going to be very useful all the time. Now, like we discussed, like if I want to treat f of x like a function where I can plug values in, then it's important that the sum converges. Okay, so like in some sense, if I think of x as being a real number, this formula only really works when the absolute value of x is less than 1. Because imagine you plug in 1, for example, right? On the left side, so if I plug in 1, on the left side, I get 1 over 0, which is obviously nonsense. And on the right side, I get 1 plus 1 plus 1 plus 1, which is obviously not going to converge because it's kind of like you kind of get a weird thing that's kind of like infinity equals infinity, but don't ever write that. So please do not write ever in an assignment or anything in a math course. Don't ever write infinity equals infinity. But you can kind of think of it like that, right? Like the right hand side is 1 plus 1 plus 1 infinitely many times. So it's clearly not converging. It's a divergent series, meaning that the sum is not a number. It's infinity or something. And on the left hand side, you get 1 over 0. And if I plug in 2, for example, it's even weirder because it's like 1 over minus 1. So it's a negative number equals 1 plus 2 plus 4 plus 8, something which is clearly positive. So this is just a warning that do not plug in numbers which are bigger than 1. Okay. And don't plug in -1 either. So you can only deal with numbers which are strictly between -1 and 1. Okay. But if you do that, if you plug in a number between -1 and 1, then this formula is actually valid. So the way the language for this is to say that the radius of convergence of this series is 1 because, the radius, basically because it converges for everything between 1 and -1. Okay. We're not going to use that terminology very often because actually most of the time when we deal with generating functions, we're not going to care if they converge or not. Okay. Basically, these generating functions are going to be a tool for analyzing sequences, and usually we won't even care. We won't ever want to plug in values most of the time, which seems weird, but that's how it's going to be. Any questions about anything so far? So I guess so far the only really valuable thing I've told you is that please remember this formula. Okay, let me kind of get you to think about this. So here's a poll. So I've told you what 1 over 1 minus x is. So I want to now know what is 1 over 1 plus x, right? In terms of a sum. So if I wanted to write out 1 over 1 plus x in the form an x to the n, I want to know what is an. So any thoughts about that? So we've got answers coming in the poll, not very many answers so far. So the way to get this one is, it's kind of a trick that we used a lot in dealing with the binomial theorem, for example. And we also use this basic trick in other contexts as well, right? So the trick is a substitution, right? So if I kind of substitute, let's say I substitute y equals -x. So the name of the variable doesn't really matter, right? But if I look at 1 over 1 minus y, that's equal to, first of all, it's equal to 1 over 1 plus x, right? Because x is equal to -y. But also, it's equal to the sum n equals 0 to infinity of y to the n by the thing up here. Just applying that to y instead of x. So this is just a simple substitution. And of course, this is equal to the sum n equals 0 to infinity of negative x. So I can put the negative x back in, and I get -1 to the n, x to the n. So the answer is, so some of you got this, that it's -1 to the n. Okay. So that's another trick that you need to remember, that you need to be able to recognize when the expression you're given, so here I gave you this expression 1 over 1 plus x, you have to be able to recognize, like, is this the same as something I know about, like this one, with a substitution. Okay, so you have to be able to notice these things. Okay, another poll. Apparently, when I was preparing these slides, I was really keen on polls. I think polls are fun anyway. It gets you guys to think about stuff. So yeah, what is a closed form? So now we're going in the other direction, right? I gave you a closed form and I asked for the expansion. Now I'm giving you, I asked for a coefficient of the expansion. Now I'm giving you a sum, an infinite sum, and I'm asking you for the closed form. So I wrote here to be careful. You don't have to be so careful. But Yeah, how would I get a closed form for this expression? So what was the trick we used last time, right? Trick we used last time was like a substitution. And something like that is pretty useful here. So what is this sum, by the way? If I write it out, write out the first few terms, right? It's, okay, so this starts at n equals 1. I guess that's the point where I'm asking you to be careful. So this is, you got x squared plus x to the 4 plus x to the 6, ... Which is kind of like, this sum here, but it's not quite, because, so there's one thing that I don't have a 1, okay? Let's deal with that later, though. Another thing is that, like, I don't have any of the odd terms. Like, I don't have x, I don't have x cubed. I just have even exponents. But if you think about it, if I just plug in, what if I plug in something here? I look at, like, I substitute y equals x squared. So 1 over 1 minus y is going to be the sum of, y to the n equals 0 to infinity, which is going to be the sum from n equals 0 to infinity of x to the 2n, which is almost there. But the annoying thing is I've got this 1 here. But then it's not too hard to shift this sequence. So if you think about it, like what I did with, remember when we were dealing with just this, the infinite geometric series, all I did was when I took x times f of x, that basically got rid of the 1, right? Because it gave you things like this, right? So here what I want to do is I want to get rid of the 1, right? Because this is 1 plus x squared plus x to the 4 ... And what I need to do to get rid of the 1 is multiply by x squared. So the answer is then going to be kind of x squared times 1 over 1 minus y, or in other words, so if I kind of resubstitute back, it's going to be x squared over 1 minus x squared. Okay, is that clear? So I know I'm getting you guys to kind of come up with the ideas here. So, but yeah, substitutions, the message here is that you have to be able to recognize how to do these substitutions. But then there's a second message here, which is if you want to kind of shift the sequence, so if you have this sequence and you want to get this one, then you need to multiply by an appropriate power of x. Okay, any questions? Okay, maybe I'll kind of, I won't spend too much time on this, but remember, so I had this thing about radius of convergence. So for the geometric series, the radius of convergence is 1 because x has to be between 1 and -1. So sometimes we're going to deal, so not very often in this course, maybe never, but sometimes you do see sequences where the radius of convergence is 0. So for example, if I take a of n, an equals n factorial, for example, there's no, so if I pick any positive x or any, non-zero x, this thing will diverge. So this, anyway, let's not dwell too much on that. But basically the message is that these kind of generating functions are not always really things you can think of as functions. They're really just a tool for analyzing sequences. So remember when we were doing the binomial theorem, we had these cool tricks where we would like differentiate the binomial theorem or integrate it. And that sort of thing works for generating functions as well. So what you can do is, so with generating functions, you're allowed to do things like taking derivatives or taking integrals. And when you do that, what you do is you apply the integral to every, or the derivative to every individual term. So what happens when I do, so I'm going to take the derivative of this geometric series. And so what I do is I apply it to both sides. So the left side is more annoying, but let's think about the right-hand side. I'm very good at taking derivatives of polynomials, right? I guess everybody likes doing derivatives of polynomials. So let's think about the right-hand side. So if I take the derivative of 1 with respect to x is just 0, then I get derivative of x is 1 plus 2x and then 3x squared, 4x cubed, and so on. So the right-hand side becomes the sum of n equals 0 to infinity of, I believe if you think about it, so what's the coefficient of x to the n. And so if n is 0, the coefficient is 1. If n is 1, the coefficient is 2. If n is 2, the coefficient is 3. So if you think about it, this is just n plus 1. Now we have the very onerous task of doing the left-hand side. Okay, it's not so bad, right? I can do this derivative, right? So it's 1 minus, so another way to write the left-hand side is like this. Okay, you could do this with the quotient rule, but I wouldn't recommend it. I'd rather do this with the chain rule. So yeah, if you think about it, the negative 1 goes to the front, right? And then you do the derivative of the inside, which is negative 1. And so it's 1 over 1 minus x squared, right? So your calculus is going to, I hope nobody took this course on discrete math hoping that they would never see calculus because, yeah, here it is. Okay. So is it clear what happened here? So from this, so this is a nice thing, right? This gave us a trick for finding the generating function of a different sequence, right? So the sequence here is an equals n plus 1. And the generating function for this is then equal to 1 over 1 minus x squared. Okay, so once you know the generating function for one sequence, sometimes it allows you to get the generating function for other sequences. Okay, I've already done this example. Okay. Well, okay, so we've done this example, but let me just remind you what it was. So it's 1 plus 1 minus x plus x squared minus x cubed plus x to the 4, etc. And we did this using, so it's by using a substitution. Now, what I want to do now is integrate this function. Does anyone know what the integral of 1 over 1 plus x is? And I'll give you a second to think about that. I'll do the other part. But while I do the other part, please let me know if you know the the integral of this. So I know what it is, but I want you to think about it. Oh, maybe we already have one in the chat. Yeah. So maybe I'll think about yeah, I guess it is. I think I guess you probably do have to put an absolute value. Let's think about x being positive, or or maybe at least -1, so that we don't have to deal with these things. So right, so it's ln of the natural log of 1 plus x, right? Because remember, if it's easiest once you know the answer, it's easy to get to check it because you just take the derivative of log of x, right? Natural log of x. Or sorry, natural log of 1 plus x, the derivative is 1 over 1 plus x by the chain rule, right? Okay, so if I integrate this side, so I get x minus x squared over 2 plus x cubed over 3 minus x to the 4 over 4 ... So this is what this tells me is that log of 1 plus x. So when I say log, I mean natural log. So ln or ln. I don't know what people call it. But this is equal to the sum of n equals 1 up to infinity of, well, so x to the n. And then what's the coefficient? It's -1 to the n plus 1. So that's just I want when the exponent is even, or so when the exponent is odd, I want it to be positive, and when the exponent is even, I want it to be negative. So I write it like this, and then you divide by n. And I hope that's correct. So now that gives us the generating function of an, which is this kind of funny expression. So again, this is just showing if I know the generating function for one sequence, I can apply substitutions, I can apply derivatives and integrals, and sometimes it gives me the generating function of another sequence. Okay, so this is actually, or maybe, so this is the sequence where a0, I guess, is 0, and an is equal to this for n at least 1, right? And so what this is saying is that the closed form of the generating function for this sequence is just the natural log of 1 plus x. Any questions about that? Okay. Yeah, so natural question is to ask, so suppose I know two generating functions, a of x and b of x. So where a of x is the generating function for the sequence an, where an is, some set of, or some sequence, and b of x is the generating function for bn. Natural question is to ask, what is the coefficient of x to the n in the product of these two generating functions? Okay, and this is often going to be a useful thing to do. So what is the coefficient of, so just to build it up slowly, so can anyone see what the coefficient of x to the 0 is going to be? So the coefficient of the constant term. And here note that, a of x, b of x, so that's the same as taking a0 plus, so just to write it out a bit, so b0 plus b1x, b2 x squared, dot, dot, dot. So how would I get the, so it's going to be something involving the a's and the b's. But what's a formula for the coefficient of x to the 0? Or I guess what I'm talking about is the constant term that doesn't depend on x. Well, if you think about it, when I multiply this, how does multiplying work, right? You multiply this thing to everything in there. So, one by one, there's infinitely many of them, but you kind of multiply it to all of those things, and then you take the second term and you multiply it to all of those things in there, right? And you add everything up. And if you think about it, the only way I can get a term that doesn't have an x is to take a0 times b0, right? Because if I take any of the other terms, they always have x to some positive exponent. So the coefficient of x to the 0 is just going to be a0 times b0. Is that clear? So to build this up a bit more, what's the coefficient then of, x to the 1? So the coefficient of just x. Any ideas? So how can I get just an x from this stuff? So there's not very many ways to get an x. So I'm not sure if people are with me or not here. But if I take, so one way to get an x, just an x without a higher power, if I take a0 here, I look at the term where it's a0 times b1x. So that's going to give me an x because it, a0 times b1x is just a0 times b1 times x. And another way I can get an x is by taking the x to the 1 term here and timesing it by b0. So the n equals 1 term is going to be a0 b1 plus a1 b0. Okay. So what I want you to think about is the whole expansion, right? If you multiply all of the terms here with all of the terms here and you add them up, how do I get x to the 1? And there's only two ways to do it. And the coefficient of x squared is then going to be, so one way I can get it is take a0 and the b2 x squared term. I could also do a1 and b1 and a2 b0. Okay, so the reason I'm going through all of this is to kind of convince you that there's a pattern here. So basically for the nth term, so the coefficient of xn, x to the power n, is going to be equal to all the ways to take, so all the k from 0 up to n, a, k, b, n minus k. Because this is all the ways if you expand the product, like you do your kind of FOIL thing or whatever, you multiply all the terms. These are all the ways that you can get x to the n, if that makes sense. Okay. Okay. So now we're going to connect these generating functions to something we did quite a long time ago in the enumeration part of the course. Do you remember this thing about cookies? So how many ways can I distribute n identical cookies to k children so that every child gets at least one cookie? Okay, and I think people got quite good at doing this. So the answer, right, is n minus 1, choose k minus 1. Okay. And remember, the fact that the cookies are identical is important here. Right, and the argument was, okay, put the cookies in a row and then choose k minus 1 points to break the cookies up, and then that breaks the cookies into k groups. Okay. Now the solution I just gave you and the solution we knew before was a very simple solution, okay? Um, now I'm going to give you a more complicated solution, which seems like very counterproductive. But the good thing about, so I'm going to give you a solution to that problem using generating functions, which, like I said, sounds like a bad idea because it was much easier to prove it just with this combinatorial argument. But there's going to be a lot of value in this generating function solution because it's going to allow us to solve more difficult questions. So where you have different variations, like, the second child gets an odd number of cookies, or the fourth child gets between 6 and 7 cookies, and the fifth child gets a divisible by 3 number of cookies, and all of these weird variations, all put together in the same question. So for that, generating functions are really useful. What I want to prove to you now is that the coefficient of x to the n in this thing, so x over 1 minus x to the k, is n minus 1 choose k minus 1. This is another thing, just another fact that I would sort of suggest you might want to memorize this, okay? Because, like always, it's even better if you can remember the reason why this is true and if you can prove it yourself. But if you can't do that, like if you're struggling to kind of understand the proof, then you're going to have to use this a lot. So it's good to like have it on hand. Okay, so let me give you a proof of this in general. So if I write out this thing, so remember, x over 1 minus x is just equal to x plus x squared plus x cubed plus etc. So if I write out x over 1 minus x, it gives me this product here, because the first term is x over 1 minus x, the second term is x over 1 minus x, and I've got k, or I guess I should say factors. So I've got k of these factors. Now, if you think about it, if you think about expanding this product, the coefficient of x to the n, well, I mean, if you think about, say, the coefficient of x, for example, if I take x to the k, for example, so to get x to the k, I have to take x from, every factor and multiply them together, and that gives me x to the k. If I want to get x to the k plus 1, I have to choose one of these things to be x squared, and all of the rest of them are x. If you think about it, this is the same as, you're taking x to the y1, let's say the first factor, so this, expression I associate with a variable y1, and I take x to the y1 from the first factor, x to the y2 from the second, so on and so forth, so that the yi's add up to n. Okay, so the coefficient of x to the n is equal to the number of integer solutions to this equation, where yi is at least 1, because all of these exponents are at least 1. So the answer is n minus 1 choose k minus 1, because we've already seen that that's how many integer solutions there are to this equation, where all the y's are at least 1. Okay, so I kind of recognize that wasn't the cleanest way of describing this, but are there any questions? So if you ever want to know what is the generating function of, what's the closed form of this thing? It is, so what I'm saying is that it's equal to this, okay? And this below was a proof of that. So this is the kind of expression that you might want to memorize. Or even better would be to learn how to derive it. Okay, so I understand that maybe people didn't like this proof. It's possible. Let's see another proof, which is kind of more algebraic. Okay, so I'm going to prove the same thing again. Okay, and I'm going to do it using derivatives. So I think actually this is probably a nicer proof. So here's what I'm going to do. I take my geometric series. Okay, we've already seen that if I take the first derivative, what I get is this. I get, on the left side, I get 1 over x squared. On the right side, a way of writing it is to say that, okay, so the n equals 0 term was a 1 here, right? The derivative of 1 is 0. But if I take the n equals 1 term, n equals 2, etc., so the nth term has a derivative which is n x to the n minus 1, okay, for n at least 1. Now suppose I take the second derivative. So what happens is, I mean, okay, this is again just testing your calculus understanding, but if you take the second derivative, it's like you get a -2 from this, and you get a -1 from the chain rule. So it's like 2 times what you had before, but then you have to take the power. So the -2 becomes a -3, and so it looks like this. And on this side, what you get is that the n-1 comes down to the front. Okay, and now we're summing from n equals 2 to infinity because the n equals 1 term becomes 0. Kind of repeating this, what you get for the third derivative is 2 times 3 times 1 minus, or sorry, 1, sorry, divided by 1 minus x to the 4. And this is the sum of n equals 3 to infinity, n minus 1, n minus 2, x to the n minus 3. Right, and so on and so forth. If I take the k minus 1th derivative, okay, let's be careful here. What you get is, oh dear, k minus 1, or actually maybe it's on the next slide. Oh, okay. So let's do the derivative. So kind of inductively, what you can kind of see what the pattern is going to be. So it's k minus 1 times k minus 2 down to 2, and let's say times 1. So for example, if I plugged k minus 1 is 3, I would get the same thing here, over 1 minus x to the k. And I get that that's equal to n equals k minus 1 to infinity, n minus 1 all the way down to n minus k plus 2, I think. And then I've got x to the, sorry, this is, let me move this over, x to the n minus k plus 1. So here I'm kind of just spotting the pattern and writing it down. But yeah, so it's, if I was proving this more formally, I would do it by induction on k, right? So I would write down the expression for, the previous k, and then I would take the derivative, and it would give me this. Okay, so now what we do is we just do a bit of algebra. So what I wanted on one side of the expression is this thing, right? What I have is this, which is close, but I need to do some multiplying and dividing, right? Because I want to get rid of this thing on the top, so I need to divide by it. I want to get an x to the k on the top, so I need to multiply by x to the k. So I just do some multiplying and dividing. I notice that the thing on the top was k minus 1 factorial. I divide by that. I multiply by x to the k, and I get this thing on the left, which is good. That's what I wanted. And on the right, I get this thing, which is also what I wanted, which is kind of magical. So this is, actually I should be a little bit careful here. So this is n, choose k minus 1, and then I've got x to the n plus 1. But I can shift my sum. I can kind of shift the, I can kind of think of, I let m equal n plus 1. Then I get that the sum, so this is a sort of a substitution on the index of the sum. So if n is equal to k minus 1, then m is equal to k to infinity. N here becomes m minus 1, k minus 1, x to the m. Okay, and then so I wanted things to be in terms of n, so I can again just write that in terms of n. It doesn't make a difference. So the n is just a kind of variable, or it's just the index of the sum. Okay, so the message here is that the generating function for this thing is x over 1 minus x to the k.